pleasant environment. Once again, we will continue our discussion. This is hopefully will set the stage for our discussion last time about the population genetics. In this video, we will talk about the Hardy-Weinberg and how we can mathematically calculate whether or not a population is evolving. This is what we call the Hardy-Weinberg Principle. So we're back to 1908, where Hardy-Weinberg law was created by these two figures, Godfrey Hardy, an English mathematician, and Wilmer Weinberg, a German physician, where they will independently identify a mathematical relationship between alleles and genotype in a population, come up with the exact same equation that describe how and under the right circumstance Mendelian genetic works, and also at the scale of a whole population. And the rest is the history about it. Hardy and Weinberg's simple equation show us the frequency with which you could expect to find different alleles within a hypothetical population that is not evolving. Hardy-Weinberg equilibrium states that in a population that is not evolving, allele and genotype frequency will remain constant from generation to generation. When a population evolves, the allele frequency in a population will change also. After we discuss about the Hardy-Weinberg law and the history behind it, next we will continue with the 5 consumption of a party 1 by the law. First is the large population size, say that the consequence if condition does not hold. In a small population, allele frequency fluctuates by the change over time, or what we call a genetic drift. Second is random mating. Same consequence with condition does not hold, but it is individual mate with a subset of the population, like for example the neighbor or close relative inbreeding. Random mixing about gametes does not occur and genotype frequency change. Third is the no mutation, also condition does not hold. The gene pool is modified if mutation occur or if entire genes are deleted or duplicated. No migration, same does not hold. No migration of individual into or out of a population through immigration or immigration. Lastly, no natural selection. Same with condition does not hold. The allele frequency change when individuals with a different genotype show the consistent difference in their survival or reproductive success. So there are 2 equations in Hardy-Weinberg equilibrium that we will focus on. We're going to start with the first one, the allele frequency, that calculates by dividing the number of times the allele of interest is observed in a population by the total number of copies of allele at a particular genetic focus in the population. The formula is the P plus Q equals 1. In this equation, P is the dominant allele frequency in the population and Q is the recessive allele frequency in the population. By the way, Hardy-Weinberg equilibrium does not mean that the P has to equal to Q, and the dominant allele frequency in any population does not have to be a larger number than the recessive allele frequency in a population. That's a misconception because dominant allele are not always the more common allele. The equation does say that the dominant allele frequency and the recessive allele frequency have to equal to 1. But what if I wanted to know the genotype frequency? The genotype frequency, a population, is the number of individuals with a given genotype divided by the total number of individuals in the population. Meaning, I wanted to know the frequency that are homozygous dominant, heterozygous, or homozygous recessive, then I can use this other Hardy-Weinberg equilibrium with the formula of P squared plus 2PQ plus Q squared equals to 1. Just like with the previous equation, I like to write what was this symbol stand for. So, P squared is the homozygous dominant frequency, 2P squared is the heterozygous frequency, and Q squared is the homozygous recessive frequency. The only thing is that when calculating Hardy-Weinberg equilibrium problem, you don't always have the P and Q values. Here ends my video presentation on this topic, the random event in population. Thank you and God bless.